Hello. So this is an example of linear probability model. So with those data, scatter plot is those dots, and then if you estimate the linear probability model for the denial, not acceptance, denial, we are estimating denial probability using 2300 observations. This is the result. So as I said, the intercept is the estimated probability of denial if the payment income ratio is 0. There is no like a real interpretation of PI ratio equals to 0 because payment cannot be 0 when you apply for a mortgage. So still, it does not matter. A probability cannot be negative, but in this data, it won't be a big problem, like as it is now, right now. And for additional probability income ratio, the denial probability increases by 0.6. 0.6 is like 60%. So if PI ratio changes from 0 to 1, then the denial probability increases by 60%. So let's put it in a more realistic context. Suppose that the PI ratio is about 0.3. 0.3, so you have to pay 30% of your income for the mortgage. By the way, so just in case, I just thought that you may don't know what is a mortgage, but if you just in case if you do not understand what is a mortgage, stop the video and search for that on Google. Simply speaking, mortgage is a loan from a bank to buy a house. So and come back to here. So payment PI ratio is 0.3, then your predicted denial probability is, just plug in 0.3 in here and you obtain 0.151. It is the probability of denial. So you are likely to be rejected with 15%, but 85% is the probability of acceptance. Similarly, we are going to calculate the same thing at 0.4, at the payment income ratio at 4, then you obtain 21.2%. So now, so when PI ratio is 0.4, that means you have to pay more out of your income for the mortgage loan. That increases the potential chance of your default, your bankruptcy. So the probability of denial increases by about 6% point, right? 6% point has been increased when the PI ratio changes from 0.3 to 0.4. So that is the interpretation of this result. This is how we interpret that, and you may extend everything we learned earlier, still work in the same way with a little bit of different interpretation. Say now I include a black dummy variable. So if you are black, then it takes 1, otherwise 0. So then denial probability increases if you are black. So like to show you how much it differs, for black applicant with PI ratio equals to 0.3, the predicted denial probability is 25.4%. So about 25%, this applicant will be denied. But if you're white with PI ratio at the same 30% level, then denial percentage is only 7%. So being black or not being white have a huge difference. that is, so this is another, this is, so our interpretation is exactly same except for the probability sense. Otherwise, we may do the same thing. Like, so this is the difference. Holding PI ratio fixed, 0.7, like 17.7% point is the effect of being black on the denial probability. So black applicants are discriminated, like in this regression results. Still, there are a lot of omitted variable biases. So, and I don't know, this is not a conclusion. Just as an example, you can clearly see that this variable has a significant result. And the mechanism the model works is exactly the same as before. So that is the main point. And then, now let's think about that. So conclusion is simple. You can use the same thing even if the dependent variable is binary. The only difference is you have to interpret the predicted outcome, and everything has a probability, which is not that difficult. So the inference method is the same. The standard errors are calculated in the same way. They will be interpreted in the same way. Like hypothesis testing can be done in the same way. Everything is the same, right? However, the problem here is basically it's linear. So previously, a linear model was good because it is linear and easy to handle. Still, that is true, but linearity may be too restrictive, too unrealistic in handling probabilities like this. For example, the difference between 50% and 51% and 99% and 100%, those two differences are equally 1% point difference. However, the difference between 50% and 51% is quite similar. Usually, say, suppose that your grade is your say SAT score, or like your income is exactly at the 50% of the whole population, and increase from 50% to 51% is actually not that difficult. 1% in this area, in this middle level, is not much difference. But from 99% to 100% is a totally different story. So maybe say 99% rich is like 1 out of 100, right? One, so like the richest friend of yours will be top 1%, but top 0% is there is only one person, Jeff Bezos, or I don't know, Elon Musk. It may change how to measure the wealth. Let's say Bill Gates. Like moving from just the most rich, the richest friend of yours to Bill Gates is a totally different world. So even though the differences are exactly 1% point difference, the difference between 50% and 51 is small, but difference between 99% and 100% is huge. That is more realistic modeling, which is not incorporated in a linear model. That's first difference. And the second problem is that another problem of the linear model is that it does not stop. It goes forever. Linear model goes straight forever. So it goes to the positive infinity, and on the other way to the negative infinity. So at some point it will always go negative and always go beyond 1. But the problem here is they must be interpreted as probability. But probability cannot be negative or greater than 1. So a linear model is not appropriate for probability prediction, because the prediction could be not a probability, or could be a number that a probability cannot take. This is why we have another separate chapter for binary dependent variable. If the linear model had no problem, then we don't need any chapter. We can study that in 5 minutes, and like we can move to another one. But these disadvantages, the problems, are too big to ignore. So we have to think about a different model. That's what we are going to learn here. We are going to learn 2 different models, but the idea is the same. The 2 models are probit and logit models. The idea is, so we have linear model, like the probability is linear. Then the major problem is it goes beyond 1 and goes below 0. And then what we are going to do now is we will squeeze the line, linear straight line, in between 0 and 1. So if it goes to negative, then make it curve and does not allow it to go below 0. So it will decrease, but it will never touch 0. And when it goes up like in this way, also squeeze it, push back into 1. So it increases, but it never crosses 1. So in the end, you will have a curved probability line, probability prediction line, like this. So exactly this is what we did. So compare this with this. Here the problem arises. It goes below 0 and it goes above 1. These 2 guys are problem. So we are going to move this back into back above 1. Say squeeze that back into the positive area and push it down below 1, so that we have this form. And of course the curve will go forever, will go toward this way forever, but it never goes below 0. Also it can go forever here, but never goes above 1. It's S-curved, nice, good looking, smooth curve. And then as you can see, in here, moving from 50% to 51% is this much difference, moving this much. But here, moving from 99% to 100% is moving like, say, this much. 100% difference is this much. So this is also consistent with our intuition. Say, here, moving here. So achieving the very best is the last 1% is the most difficult thing to do. So that is also reflected in this curvature, in this curve. And this is cool. So depending on how you draw this curve, we may have a probit model or a logit model. It is just how you curve it. Like if you draw it a different way with a slightly different curvature, then you may get a different model. So pretty much these 2 are doing the same thing in reality. So I will explain how they differ, but your choice is, you may choose whatever you like in practice. Okay, I will stop here and I will explain these 2 models in more detail in the next video. See you later.